Yeah, the slides are going to be in French. I believe you understand French a bit? No? Mostly English? Or only English? Okay. So, microscopie optique générale, so the general optical microscopy. It's easy to figure out, right? Good. And Dominique Fignon is my name. Par is by. Dominique Fignon. IRCM, you know, it's Institut de Recherche Clinique de Montréal, which translated would be Montreal Clinical Research Institute. I think we're not allowed to say that. But it's Institut de Recherche Clinique de Montréal. Okay, so presentation plan de la présentation. We're going to see mostly lights and properties of light. We're going to see what are the characteristics of an image, what kind of system we can use to detect light, the principal component from a microscope and the limitation, and contrast techniques, which is mostly what we try to do when we look at the specimen, because usually the specimen is like translucent, so if we want to see it, we kind of need to make it contrasted. And advanced technique of microscopy. So, optical microscopy. So, those are two words. So, optic. Optic is the part of physics that plays with light, with electromagnetic waves. Okay, so it's a bit different than electron microscopy, which would play with electrons. Now here we only play with light, which are photons, and that's basically what we do. And the advantage of using optical microscope is that we can still keep the specimen almost alive, contrary to an electron microscopy. An electron microscope where you need actually to shoot electrons into your specimen, and for that you need to put your system into an empty place. So the specimen needs to sit in an empty vacuum, because electron will be absorbed right away if it's in the air. Okay? So that's a big advantage of being in a normal environment, a living environment. And microscopy is just to observe something with a lens system or any system which would allow you to see things that you're not able to see with your eyes. And so we're going to have a look about light property. I'm going to go fast over it because I think it's nice to know, but it's not, we're not going to pass all the course over it. Sometimes it might be difficult to understand everything, but at least just to have a look at it is good, and just bring some idea about it. So the electromagnetic spectrum, so most of the time we will play in the visible range. So that's the light that our eyes are able to see. But there's a lot of electromagnetic waves that our eyes don't see, like X-ray or gamma ray, even ultraviolet, UV, which is kind of the light also. We don't see it. And there's the microwave, and even all the wavelengths that are used for communication. It's really in a long range, so we don't see it. So we only see a small portion of it. And so this is the visible range that starts about 400 nanometer up to 700, 750 nanometer. And then after it's infrared, and below it is UV, and even X-ray or gamma ray, which are much more energetics, which will damage you if you are hit by that. Okay, so just to know that. And so since it's a wave, its propagation goes at light speed, c, always. But as photons enter matter, they will be slowed down. Okay, so in water it's going to be much more slowed down, and in oil also even more. So that kind of defines the index of refraction. Okay, so the index of refraction of something is the way it slows down light. Okay, so and usually we will talk about refraction index of translucent things, so things that does not absorb light but just refract it. Okay, our body will absorb light, so that's why we don't see through. But most of living thing we are looking at, if it's really thin, then it's not going to really absorb. So if it's in water, so most of what we are made of will absorb light, but some of wavelength will not be absorbed. And this is also why, so it's good that it's a red pointer because it goes through my finger, but if it was white, it would be also red, since it's only the red part that go through. So infrared are really translucent, they are not absorbed by living thing. And that's why we will use those a lot when we use probes. So we will shoot some red light and take out the infrared, and so it penetrates well and is also well detected. An aspect of light is polarization. So light propagates into certain direction. Okay, so usually a source will emit light in all direction except for lasers. Lasers, they will be in a certain polarization, mostly because all photons are in the same group and will have some properties which we define as coherence. Okay? And so the polarization will be used in many systems and will be used mostly for contrast, because if a polarization has a certain, well, it will have a certain angle, but we can distinguish it from another angle by using what we call a polarizer. Okay, and this is mostly how those screens works. It works with polarized light. Okay, so if you and it uses what we call well, what are liquid crystals. So liquid crystals can align in a certain direction or be just everywhere. So when it's everywhere, light go through. But when it's aligned, then it doesn't allow light to go through, and this is why we see kind of something black, or we don't see light. So a computer screen has light everywhere behind, and every pixels will be filled with liquid crystal, and voltage will control the alignment of those liquids. And so the light will go through or not. Okay? So that is polarization. Refraction index, that's a bit what I said about the index of refraction is light speed over the speed that it goes into that medium. So index of refraction will always be greater than 1. Okay, because this is maximum, and here it's going to be slowed down, so smaller number. So this one is going to be over 1. And in glass and water, it's going to be different. So water is about 1.33 as refractive index, while glass is about 1.5. And so light, which is composed of, let's say, white light, so all the spectrum, it will be refracted in a prism like that, and that's what gives the arc-en-ciel, what is it? Rainbow. Thanks. Okay, so that you know that arc-en-ciel in French is rainbow. Yeah. Okay, so diffraction. Diffraction is the way objects will make the light going in many directions. So objects will diffract light, and diffraction, when there is diffraction, there is going to be also interference, interference into that, and so a wavelength which would be planned going into a little aperture will become circular like this and make some patterns of interaction. Interference. Okay. So interference. Interference can be constructive or destructive. So two wavelengths going in the same, what we call phase. So if waves are going at the same time, it's going to be a summation. So the composition of this will result into a higher vibration amplitude, while destructive would be something which is out of phase. So when you add it, it's going to be something really small. And that's how we can bring some contrast. And another properties of light is the duality. So at the same time, light is an object, you could say, and at the same time, it is also a wavelength. So it behaves the same way depending on how you measure it. And so light kind of bring energy. So it has what we call momentum in English, quantité de mouvement in French. So the momentum of light is P, so it's the energy over light speed. So that if you have the drawing is not good at all, actually. It would be those that would go there, because the photon will be absorbed by black while it's going to be reflected here. So those two should be there, and this one there. Sorry for the drawing, which is not good. So this one will not, so it's going to be also the opposite. So totally wrong. Yeah, the photon is going to go there and be absorbed. So it will be taken by this one here. So it's going to go this way, because this one's going to be hit by the photon, while here it's going to be a reflection. So there's going to be no punch. And so it's going to turn. And so this needs to be in an empty, but if you put a flashlight over something like that, it's going to turn. And this is the Young experiment, which was done with an electron, because with electron you can control how many you output. And so the experiment was an electron that has the choice to go in one or the other slot, and then it would hit a screen, and while it hit the screen, even though it's only one particle that goes at the time, it interferes with himself and produce an interference pattern. So that's why we say that photons will behave also as a wave and as a
I can get it.
yeah, this one.
Yeah.
Okay. So the thing is that, but I think we could do it's just a drawing here, but we could do it with real thing. So if you have a device that can throw electrons, and you have a little slit, so you have two slits, and then if you shoot only one electron, the electron is going to go either there or there. It cannot really go both at the same time if it's only one electron. So, and the electron is going to hit the, yeah. And so it's just to say that if it hits, it's going to go somewhere, and if it goes into the other slit, it's going to go also somewhere else. But it's just to say that if you produce a lot of data like this, you're going to have an interference pattern also, which just occurs by the fact that the electron will kind of interfere with something that made it to go at a certain position, and some other position are kind of not allowed. Okay. So but to make a calculation, to have this pattern here, you need a lot of data. You cannot say my electron is going to go there this time, and then it's going to go there. You have kind of a pattern that, to calculate this pattern, you need not only one electron, but many of them. And so the pattern that you're going to calculate, you're going to know that here there is no possibility that it occurs, here neither, here. And so that you're going to have that pattern. But it's just to understand that at the same time that it is only one position that it can arrive, if you reproduce the experiment, you're going to end up with a pattern which would say that.
Give me an example of the structure. It's hidden. Give an example of the structure it's hidden in the first place.
Sorry?
The electron patterns and the second, say backward, will give me an example of an idea about the structure of the protein, for example.
If we go, let's say, into super resolution microscopy, which is actually a nice topic. Maybe I can have, I'm not sure if I do have it here. Maybe I'm going to come later over it, and you will understand more. So that's basically what we do also when we do super resolution microscopy now, because we are counting photons, or we can measure it with more precision by having more data of a single fluorescent molecule, and then but this pattern will also grow up like this. And so let's say the example would be is that if I measure only one fluorescent molecule, and it goes, instead of going into this slit, it's going to go into my objective, the objective that I'm using. And since it's going into an objective, it produces a diffraction pattern also. And this diffraction pattern, while I'm getting more photon, it's gonna be much easier to figure out where is the center. So let's say I only have this image here. So this image, I can figure out that the center is about here, maybe. And if I go here, the center is, it's much easier to figure out that it's here. And with this one, I would say that since there are 1, 2, 3, 4, 5 lines, so the center must be somewhere around here. So it's much easier to figure out where is the actual position of it if I get many datas instead of having this. So that's how we can also figure out with super resolution microscopy. So we take the fact that light is a wave, and we know the pattern that it should produce, and so we can figure out with more precision in the center of it. So yeah, but I will re-explain it with the super resolution thing. Yeah. So, and fluorescence, so this is a concept that it's used all the time in microscopy nowadays, mainly since they discover the green fluorescent protein from the jellyfish. So this event was really something that made microscopy techniques really used and give a nice image. Okay, so so it's really important to understand fluorescence. So we shoot a certain wavelength onto a molecule. So and so the electron will absorb the energy and be into an excited state. Okay, and this excited state will stay a certain time, and after this time, which is not really long, it's about 10 to the minus 9 seconds, so it's pretty fast, huh? But at the same time, it's pretty long for those molecules because the time that it takes to absorb the energy is 10 to the minus 15. Okay, so 10 to the minus 15 is 15 zero and a 1 of a second. Okay, so it's pretty short. And so it's so short that it's also the uncertainty principle. So you don't know where is that molecule exactly. So it takes a certain time to figure out that, oh, it has been absorbed. Okay, and so so absorption 10 to the minus 15. So the other one is 10 to the minus 9. So it's 10 to the 6 difference. So the absorption can happen 1,000,000 times while it's going to go down and shoot a photon. Okay, so you can have 1,000,000 absorption at different time, and then a photon is going to be produced by fluorescence. And when we use a confocal microscope, we shoot a laser. The amount of time is 10 to the minus 6. So 1 microsecond. Okay, so 1 microsecond is still long because we can see about 1,000 fluorescence event in 10 to the minus. So fluorescence is really something really fast. We turn the light and then we see it right away because our brain sees about 15 images per second. So it's really long compared to those events. Okay. So now we are into the characteristics of an image. Is it okay if we make a pause around, let's say 10 or 10:30? We only make one break. Is it okay? We split it in two? No. Yeah? Okay, or tell me when you're tired. We're going to make a break. Take another coffee and come back. Okay. So, image characteristics. So what are the characteristics of an image? So, the resolution is something. So the precision of the element that constitute our image. The contrast. So if we can distinguish things that are just beside each other. Here I say grandissement and grossissement, which is a little bit different, and it's mainly about definition. Okay, so I would say it's mainly about definition here. But it's also a good thing to understand. And maybe I would say distinguish also from photography or taking an image with a microscope, because they are in microscopy it's much more defined, I would say, than in photography, because when you take a picture of something, you will never get the scale into it unless you put a rule into your image and say it is at this position. But if I take an image of the moon, if I know that I'm on Earth and I get that zoom and things like that, I can figure out the size of the moon. But even there, if I adjust my zoom and things like that, so if I'm here and I take a picture of the phone, I cannot know the size of the phone. Okay, and so into a microscope, when you take an image, if you have an objective that has a certain magnification, then the magnification is defined from something, and this is mainly, here the grandissement and grossissement. So grossissement will be defined with an angle, while the grandissement is really defined about the size of an object and its image. Okay, so it's mainly grossissement will be with an angle. Okay, so mostly, and when you take an image in microscopy, the distance at which you see the image is defined to be 25 centimeters. And that's how we can know the size of an object, because it's defined like this. Okay, so resolution. What limits us with resolution? So it's mainly light, and light has a certain size if you look at it at a specific time. Okay, and so this pattern here is the Airy function. So that is the pattern produced into a circular aperture. So this pattern will be produced by any dot of light that go through an objective. And this is what limits us into resolution. You can think about resolution like a pen. If you have a pen that has a large tip, when you write with it, you cannot get a really nice writing. You will be limited to some size. So if you have a large tip, you're going to draw big letters if you write a message. And if you get a really sharp tip, then you can do many detail in your image. And the same thing happens with objective and also the wavelength of the light that you use. So the wavelength will limit the size of spots that you're going to see into an image, and the aperture of your objective will limit the resolution of those spots that you look at. Okay, so and so the aperture is something really important to understand or only remind. Okay, only reminding that is a good thing, so that if you have a high numerical aperture objective, you're going to see much more detail than if you use a low numerical aperture. And this is also just information you can get from something, and you can look at it like that, is that having a big aperture is something that you can collect large amount of light, while here you see it's pretty small. Okay, so if I make a circle here, so if I have if I have something that emits light from here, okay? So I'm an emitter of light, and I sit here, and I throw light everywhere, so I can throw light like this everywhere. That's what happened with the fluorescent molecule. It emits photon in any direction, no privilege one. So so you can see that with this lens here, you're going to be able to collect that angle. Everything that goes here, not collected by this lens. There, it's not collected by the lens. Okay? But if you get an objective like that, oh, here, everything which is emitted in this range here, you're going to be able to get it with this one. And even with this one, it's much larger again. Okay? So you see that the more light you can collect is really with the aperture size. Okay? And so you can also see that if you bring this lens here, you're going to get an even wider angle. Okay? So as the lens is closer to your specimen, you are able to collect more light. But there is something that if it was the case, then every lens would be really close to the specimen and that's it. But what if you have, let's say my finger. I want to put my finger under a lens that is, let's say, at about 1 millimeter. Then it's going to be difficult maybe to enter my finger in between the system that shoot light over my finger and things like that. So it's limited by the size of the object that you're looking at. And the thing is that a lens in microscopy is different than a lens of a camera like this. Okay? So those camera, or even this device, it's mainly a lens that you play with the distance in between each lens. Okay? Into an objective, everything is fixed. And when you use an objective of microscope, the focus is always at a certain distance from the surface of it. Okay, so if I make the focus with an objective, actually I just bring the objective at the right position where the focus is, and then I see the object correct. Okay? So the focus is always at a certain distance from the lens, and this will define also what we call the working distance. So you remember when I said, will I be able to put my finger in between this? So that's what we define as the working distance, is the place that you have between the surface of the objective and the place where the real focus is. Okay? So that is about resolution. Contrast. Aha. Yeah. So contrast has something to do with the specimen and the background. Okay? So into an image, usually we will be able to define what is the object and what is the background. Usually. Sometimes it's difficult to figure out what is really the object and what is really the background. It's either it's either one or the other. But at the same time, you need to have a certain contrast in order to say, oh, this is my object or this is my background. Because if it's everywhere the same thing, then you're going to say I only have background and I don't see the object. Okay? So, and every color is going to be a bit different also in terms of contrast. If you have something blue with a black contrast, it's not going to be the same thing that green with a black contrast and red with a black contrast. And this is mostly because of our eye. Okay, but I will go there really soon, actually. Right there. Okay. So, grandissement, grossissement, I've talked about it a bit. So it's mainly a thing of angle and definition. Okay. So, detection systems. What can we use to distinguish light or to capture light even? And the first thing is our eye. And so it's really important to understand our eye first, and then we can understand the other systems of detection. And so our eye, from elementary school we learn colors and things related to that. And we also learn about primary colors, and I would say that most of the time we don't really know. We understand that there are 3 primary colors, and that it makes, we know that the summation of colors gives light. And I would say that most of the time we don't really understand why, and we say, okay, yes. And then we take some paint and we mix them, and oh, it's black. And why is the summation of all colors gives not white when I mix my paintings? And so there is another aspect that is really important to understand is absorption and reflection. Okay, and in terms of absorption, it's pretty easy to understand, and even reflection. But with reflection, there is the concept of you need a light source also in order to produce a reflection. And so there comes also, I would say, is it something that emits light or just take light? So a screen like this, and even here it's only a reflective screen. So the light source is there and shoot the light, and because the screen is white, then the colors appear pretty good. But if I take the same thing and shoot it onto those red door, it's not going to be really good, because the absorption is only for red. Actually, no. If I see red, it's because it reflects red and absorbs 2 other colors. Okay, so and so we also need to understand that primary colors only comes from our biology. It's only because we have red, green, and blue detector. If we had, let's say, 4 detectors, then there would be 4 primary colors. Okay, but the primary colors are just because our eyes is made like that. It absorbs blue, green, and red photons in a certain amount, and then it shoots out in our brain a certain color depending on how the amount is done. Okay, so primary colors. There is the reflection thing, or actually if it emits red, green, and blue, when it emits red, green, and blue at the same time, it gives something white. And it's mainly how those screens work, is they have 3 color emission, and if you look at a screen like this under a microscope, you're going to see the, I think I don't have it here. Yeah, I should put it into the presentation. Another one. I'm going to show you also. Or we can go at the microscope and just take a look on the screen like that. It's nice. Yeah. Okay, so and so there is also the absorption. So when we play with paint, primary colors are really yellow, cyan, and magenta. And this is because yellow actually absorbs, well, what is it again? I'm always mixed up. When there is 3 things, then it's mixed. Okay, so when you have, so you have a white source that goes, and then blue is absorbed. Yeah, so that's why it's yellow. Okay, so it absorbs blue, So you have green and red that is re-emitted at the same time, and it gives yellow. Okay, so this one. So cyan, it actually absorbs red. So if you shoot white light over something which looks like cyan, it actually shoots back green and blue because it absorbs red. And the magenta will absorb the other one. Magenta, where is it? It absorbs green. And so if I shoot white light over magenta, then since it absorbs green, I will see again red and blue at the same time, which is magenta. Okay? So if I mix up all those things, I'm going to see black because everyone will absorb one of the primary color. Okay? And so basically, when you have an ink jet machine, you play around with all those three primary colors. And they also add black ink because at some point, if you only add a certain amount of black ink, you're gonna use less those three colors, because when you need black, you need kind of those three at the same time. So you just shoot black instead, and then you get the equivalent of having those three, and then you only use two ink in order to get a difference in the color. Okay, and then we are close to the break. Is it okay? Yeah? Okay. I think we can make 2 breaks. It's going to be better. Usually I do only 1, but now I feel good to make 2 breaks. Okay. So, signal analog versus numerical. So, it's also good to distinguish this thing, even though it's everything in those days are numeric. Yeah. There is something. Well, there is always something analog into that, and then you need a digital converter. That is basically what you use. So if you have a really nice digital converter, then you're going to be able to distinguish. Even that curve is not really. It looks a bit more analog than this, but still we see the pixels. So I would need a retina display over that kind of device in order to get the really smooth curve, so that your eye is not able to see the bump of the pixels. But does not exist yet, or maybe it exists, but we don't have it here. Okay, but so the thing is that an analog signal will always be pure, I would say, and then you convert it to something digital. And the way you are able to get details into this signal will make your converter a good thing, a good one, or not really good. Okay? And so basically to get a digital number, usually, well, not usually, but it's like this, it's mostly binary thing, so it's either a 1 or a 0. And every of those bit, actually, and so here it's only a 1 or a 0, and here it would be 1, 2, 3, 4, 5, 6, 7, 8 bit converter. Okay, so I get 8 bit for one value. So it's 2 to the power of 8, and 2 to the power of 8 gives 256, sorry. So the number that I'm going to output at the end is going to be between 1 and 256, or in image, usually we keep 0 at some position, so it's from 0 to 255. So an image of 8-bit data, each pixel would have a value of 0 or 1 or 2 or 3 until 255. Okay. So, so digital camera would have red, green, and blue component for color, or you can have only a gray array. Okay, and so the value there. So since it's black would be 0 and 255 would be white. So in between 128 and below this would be, let's say 29, 30, 31, 32, 33, 34 would be this range here. And if I get a color image, then I would have for each pixel a red, green, and blue component. If my image is red, so here in that range, I only have red, which has 168, 169, 70, and 173. So this is a high composition of red, but green and blue has 0 value. So it appears only red. And if I get a color image. So let's say I take this region here and bring the pixel value. If something looks like, it's mostly like blue, so the blue component is greater, 234. There is still red and green data, so, and a white pixel would be 255 for every value here. Something which is darker would have low red, green, and blue component. And something red would have a greater red component. Here I don't really have green pixels, so the amount of green is always lower than something else. And so a digital camera, to look at color thing, so it uses CCD. You always hear that, CCD camera. So the CCD is the chip that where the photons arise. Okay, and each pixel is compound is made of a little charge-coupled device that receives the photon and convert it to an electric current. Okay, and every pixel usually here it's going to be called a Bayer pattern. So you have pixels which are better to detect green, and other pixel which will detect the red, and other the blue. And why they do put more green is because our eye is more sensitive to green, so it's better to detect, better detail the green. And so the difference between the CCD, charge-coupled device, and the CMOS, nowadays the CMOS are better those days, and they are almost as good as CCD to capture light even. And they do have the advantage to get their own circuit. Okay, so while the pixel get the data, it transfers right away the data to the device or the computer. Okay, while when you use a CCD, let's say this pixel capture a certain number of photons, it will transmit this data to the other one, and then the other one, and then the other one. So the first one gives the data to the computer, then the other one takes the data from the other, and so you need a certain amount of time to empty all the data that are into the device. While a CMOS, every pixel will give its value right away to the computer. Okay? So it's much, much faster. CMOS will capture data ready. Well, they capture at the same speed, but they transmit the data in a really most efficient way than the CCD. Okay? And now the surface that detect, I think that the circuit now is behind, but in previous version there was a certain area where it could detect the photon, and the circuit would take also a certain space. So that's why CMOS were not as efficient, because the CCD was all the surface which was effective to capture. Okay, well, okay, yeah, I think we will stop with the photo multiplier tube. Photo multiplier tube, yeah. So those devices, they just count photons. So as a photon arises onto its surface, there is an avalanche of electrons which will amplify the signal. And so those devices are really sensitive. And they are also really fast. Okay, so this is the kind of device we use with the confocal system. And we will see it after the pause. It's okay? So we take a little break, about 5 to 10 minutes. So we come back at 10:05, between 10:05 and 10:10. That's good?
Yeah.
Okay, good.